Hi, my name is Vladeta stojanovic, and today I'll be talking about ontology-driven analytics for indoor point clouds. Point clouds can present a snapshot of reality and are useful for capturing the current state of the physical environment. This makes them useful for use as base data for as-is BIM model generation or digital twin data. Since point clouds are ambiguous by nature, they need to be semantically enriched in order to make them useful. Methods for semantic enrichment vary depending on the use case, but most commonly include segmentation, semantic segmentation using deep learning or machine learning, geometric reconstruction, and spatial deviation analysis. Here is an example of semantic enrichment of indoor point clouds, which have been captured using a depth sensing device such as a mobile phone, and with this generated point cloud, we can then perform segmentation, geometric evaluation, and classification, also including additional data sources such as sensor data. This leads to the point cloud being semantically enriched and enables stakeholders to use this point cloud for decision making, specifically within the realm of facility management and real estate 4.0. However, there is a problem with using such a semantic enrichment approach. That is that automated processing, semantic enrichment, and visual analytics methods for point clouds are often use case specific for a given domain. Use cases often use a one-time pipeline or process configuration for semantically enriching point clouds. This requires the design, development, and implementation of different point cloud processing pipelines and configurations for every different use case. An ontology-driven analytics approach can be used to solve this problem. So the solution is therefore creating and maintaining a knowledge base and utilizing an ontology for inferencing optimal selection of automated processing and analytics techniques for point cloud data. We present an approach for an ontology-driven analytics for indoor 3D point clouds that supports semantic enrichment, smart representation exploration, and processing. So I will begin briefly by giving an overview of what are ontology-driven analytics. An ontology can be used to define the relationships between entities, methods, data, semantics, and processes for a given domain. An ontology can be used to set up and maintain a knowledge base and for performing related inferencing operations. This can be used for selection of optimal processing and analysis techniques for point clouds for indoor environment representations within the subdomain of operations and maintenance in facility management. So what is an ontology? An ontology is a representation of object relations, their properties, and processes used between them, thus allowing them to be described formally within a given domain. A knowledge base contains all of the semantics, rules, and facts used to infer a decision based on provided ontology, usually with ontological metadata. As such, a knowledge base employs a given ontology to structure its data. When the ontology is updated by various processes and results and inputs, examples, domain expertise, computed semantics, etc., so is the knowledge base with new rules, facts, and associated semantics. Thus, an interdependent relationship exists between the two concepts, as they are both used to contribute to the definition, creation, and updating of knowledge within a given domain. Semantics are used to describe relationships between different processes, objects, and ideas. It is essentially the study of meaning. Semantics for point clouds can be thought of as adding human interpretable meaning in terms of visual and textual attributes, such as colors of points, names of point clusters, etc., and establishing a relationship between them. Thus, the semantics of point clouds and the relationship between them and other entities such as floor plans, BIM models, CAD data, or other documentation can be added to a knowledge base. A system can then use this knowledge base to infer new processes and generate new semantics for new input data, such as point clouds of a new building or an indoor environment. We present and discuss a conceptual system and process design for each of the key components for an ontology-driven analytics system architecture, which would enable the feasibility of such a system for further implementation. The approach will be implemented with service-oriented paradigm. A conceptual system architecture for semantically driven inspection and analysis of indoor point clouds is also presented. We also discuss all of the key system components. which enable us to derive useful semantics based on the presented ontology. This includes a database management system, visual analytics, an algorithm library, a query component, a processing component, and a knowledge base component. We will briefly discuss each of these components. The first one is the knowledge base component. The knowledge base component utilizes the existing semantics objects to form a decision based on an input query. This can include selecting an appropriate algorithm for processing data in order to generate the predicted type of result. It would link all of the previously generated semantics in order to infer a suitable set of parameters for processing of point cloud data in order to satisfy the interpreted conditions of the input query. This could be accomplished using, example, Bayesian networks. All of the knowledge is based on semantics that will be stored and accessed in a database management system. The database management system component is used to store all of the generated semantics that are the results of the semantic query operations. This includes examples, attributes associated directly with the point cloud data, or parameters for processing a specific kind of query, such as segmentations of walls in a building. These associated semantics would then be sent to the database management system component in the form of standardized semantics description object, where they would once again be utilized by the knowledge base component next time a new task is initiated by the user. Such a database system could be a relational or non-relational database management system oriented towards semantic spatial queries and generalized semantics. The algorithm library component would contain all of the required algorithms for semantic enrichment of indoor point clouds for facility management applications. This may include algorithms for segmentation, reconstruction, or semantic enrichment using supervised or unsupervised machine learning methods, such as clustering or semantic segmentation using deep learning approaches. The selection of the appropriate algorithm would be decided by the knowledge base, based on the user's query and previously generated semantics. For example, if the user query is to find all the walls within a given point cloud representation, an algorithm using the ransack segmentation method, for example, could be used to find all the points fitting a planar surface in the current point cloud. The query component would interpret the user's query in terms of textual strings and then send this to the knowledge database. The query could be as simple as to find all the chairs in the room, and to a more complex conditional statement, such as using some sort of scripting language. For example, if you wanted to find all the points in the point cloud that correspond to planar surfaces, and then use this calculation to actually generate some sort of graph that would then be used to form a connectivity graph to show all the rooms in a point cloud representation. The processing component applies the selected algorithm to the point cloud data along with specific parameters as determined by the knowledge base component. The results of the processing component are then sent to the visual analytics component for presentation to the user, and the database management system is used for inclusion in the knowledge base and to be used by the knowledge base for future decision making. The processing components would also be responsible for selecting the distribution and computation model for the required tasks, for example using a multi-GPU approach for intensive tasks or cloud-based computing. The visual analytics component is responsible for the generation and representation of the various visualization results. Visualization of the semantically enriched clusters of a point cloud scene is vital for highlighting their location in 3D space and bringing them to the attention of the user for further inspection and assessment. In order to draw the user's attention to areas of interest in a point cloud that may contain a lot of visual clutter, we can consider the use of visualization idioms. Example given for highlighting and possibly abstracting through visualization the spatial areas of interest in the point cloud. We will now show some of these proposed concepts in terms of illustrations. We begin with an ontology example where a user puts forward a query which is to find all chairs in a given point cloud representation. And as you can see here, we present an ontology consisting of all the main classes, methods, and attributes, including instances and associations with each of the different entities that form the core ontology example. The next example is of the semantics visualization, where we show some basic visualization idioms such as highlighting segmented clusters in a point cloud scene, which may have been generated using semantic segmentation with deep learning, and presenting these to the user, so that the user is then able to see which of the point clusters represent objects such as chairs, tables, and desks in a common office environment. Additional visualization idioms are also presented, which may include specific color coding of clusters, transparent visualization depending on the view angle of the point cloud, as well as using simple 3D geometric shapes in place of these segmented point clusters. We have now reached the conclusions in the Outlook section. We have presented and discussed a conceptual system design for ontology-driven analytics of indoor point clouds. Such a system would benefit facility management stakeholders by enabling them to gain insight into the as-is state of a building, while simultaneously updating and contributing to the knowledge base used by the ontology-driven approach. We conclude that an ontology-driven analytics system can be designed, implemented, and deployed, provided that a suitable ontology of buildings and indoor spaces can be established. We also have to consider that such an ontology may be specific to geographical and social conventions of what can be defined as a typical office building. We are currently working towards developing a working prototype of the full concept proposed in this paper. Thank you for your time, and I hope you enjoyed my presentation.